One last little piece on the integral test for convergence and divergence of series, and that is the estimation and remainder theorems for the integral test. So remember, when we test a series and we determine convergence or divergence, all we know is whether the series has an actual sum, a convergence, or it does not, divergent. It doesn't tell us what exactly that sum is. And so that's where we get into what are called estimation theorems or remainder theorems. So in this case, for the actual integral test, this is what the remainder estimates say. It says that if we have a continuous positive and eventually decreasing function, so these are the conditions that need to be met to even apply the integral test, on some interval from n to infinity, then if that particular series is convergent, so if we've shown that that series is convergent, we would use the integral test to do that, take the integral, then it has a sum. So it has some value s that would be the sum. So this is the actual sum of the series. And then s sub n would be the partial sum. So if we use n, say 10 terms to estimate the sum, then what is the error or the remainder when s sub n is used? So what would be that actual error? The error if we were to use the first n terms. Well, that is bounded by two integrals, and we know how to compute integrals. So the actual error is bounded below by the integral from n plus 1 to infinity of f of x, and above by the integral from n to infinity of f of x. Now, to be honest, we really tend to only care about the right half of this inequality, this piece, because we tend to want to be bounding our error, our remainder, with an upper bound. We don't want our remainder to get too big. We want it to be less than or equal to some value. So that said, we can then actually find the bounds for the exact value of the series, as we've said here on this last line. So notice here, this is actually saying then that the actual series, or remember, if it's a converging series, it has some sum s, is bounded by the partial sum plus, on both sides, the partial sum plus integral from n plus 1 of f of x dx, lower bound, and above, again, the upper bound is what we tend to care more about, and that upper bound is the partial sum plus the integral n to infinity of f of x. Okay, so that's what the remainder estimate says. You can see right here why that works. You can see why building those two, that you can see the integrals, the gray area, and why building those two summations for the r sub n can be shown here. So that little graphic shows why that theorem in a visual representation is true. And I wanted to just write one more thing over here. So just keep in mind, if we use, so here's kind of the little summary of all of that notation and mathematics that we just talked about. So if s sub n, right, the nth partial sum, so if s sub n is used to estimate the sum s of a converging series, and I'm going to call the series, I'm going to use a different index from k equals 1 to infinity of a sub k. Now, I'm not going to write up the whole piece about the fact that we've used a positive, continuous, eventually decreasing function. We'll assume that's the case since we're talking about the integral test here. We're just going to say if we've shown all of that, we have a converging series, converging series through, I'm just going to write through the integral test. Okay, so it meets all those conditions that we've been working with for the integral test. Then we can say this, that the remainder r sub n, which is just the difference between using that partial sum and the actual sum. So when I'm putting absolute value around here, so it's the partial sum minus the actual sum, that is what we call the remainder. Or you can actually think of it as the error in using S sub n as an estimate. Okay, so that's the error. Okay, and that R sub n is bounded by two integrals. Again, we're more interested, and we will utilize the right-hand side of this inequality that I'm going to write right here. This is what we're more interested in, but it does actually have a lower bound as well. And we could say that the integral from n plus 1 to infinity of f of x dx. And sometimes we utilize that. We would utilize that on the second inequality if we were to actually take that remainder and say, well, oh, that's right, that remainder is actually s sub n minus s. And put this all back in, put in the rest of this inequality back in, and actually look at it like this. Now remember that this absolute value is the same as saying s minus s sub n. So we can say those two things are equivalent because we've used the absolute value. And we could say this. We could say s is, the actual sum is actually bounded. So remember, that's the actual sum. It's bounded by s sub n plus the integral from n to infinity of f of x dx, and s sub n plus the integral from n plus 1 of f of x dx. And what we're looking at, what these integrals are, these are what we could think of as actually the tail. Okay, we can think of this as the tail of the integral. Right? If we've used, and this is also the tail, this is the tail of the integral, this is also a tail here as well. Okay? This is a little shorter tail, n to infinity is a little longer tail. This is the tail, like if we have used n terms to make an estimation, then how much is left over? Well, that's the error. That's what we think of as the tail of the integral. Okay, so all of that, that's kind of just a quick summary of that theorem that we just talked about, but what we're looking at is actually using this to make some estimations for the value of a converging series. So let's take a look. This is an example that we actually looked at as one of our examples for the integral test, and we showed, okay, we've already done this guy, the series from k equals 1 to infinity of k e to the negative k squared. We've already shown, okay, we showed this converges by the integral test. And we used f of x equals x e to the negative x squared. So we've actually already shown with this particular series, we've already shown that this guy converges. You can look back at a previous example on that one if you want to see. We've already shown that this converges, and we used the function x e to the negative x squared, and we were able to show that that function is continuous. Remember the three conditions: decreasing and, continuous, positive, it is decreasing too, positive, and eventually decreasing. You have to show those three conditions. Done a couple examples now with the integral test, but you have to show those three conditions are satisfied by the function, and then you can use the integral test to show that it converges or diverges. All right, so if we've already done that, so we're going to skip over that part. That was shown already in a previous example. We're going to skip over that part, and now we're going to do this part. Let's find the value of n that would be required to ensure that the sum is accurate to 0.0013 decimal places. Okay? So to the 1,000th decimal place, 3 decimal places. And then once we've done that, once we've figured out how many terms we must add up for the partial sum, then we'll actually find that sum accurate to 3 decimal places. So how do we do that? Well, we're going to do that by looking at the remainder. And we're going to say, okay, well, if I need, I'm going to shrink this down just a little bit so it's all on one page. If I need that, so for part A, so let's do part A first. So I need that to be I need my sum to be accurate to 3 decimal places. So 0.001, by the way, is equal to 1 over 10 to the third, 1 over 1,000. So we want to be accurate to that amount. So we want R sub n. We actually want our remainder, which we know our remainder from the theorem. We know that our remainder is going to have to be less than or equal to the integral from n to infinity of f of x dx. We'll put in our f of x in just a second. We also know the other side of it, that remainder is also greater than or equal to n plus 1 to infinity of f of x dx. This is the remainder, or you can think of this, the remainder if we used n terms, or you could think of it as the error in using n terms to estimate s, the actual sum. Okay, so this is the remainder or the error in using n terms to estimate s. So if that's the remainder, well, that's what we want to be less than or equal to 0.001, or 1 over 10 to the third. That's what we're trying to bound. We're trying to say we want this remainder, this error, to actually be less than 3 decimal places. So again, I mentioned when I was kind of running through just the theory behind the remainder or the estimation here, but this is really the side of the inequality that we're looking at. If we want to bound the remainder, we want to bound it with an upper bound. Okay, so we want it to be less than some value. We don't tend to say we want our remainder to be greater than, or our error to be greater than some amount. So we're really going to focus more on this right-hand side of this inequality. Excuse me. So let's get in there and do it. So we already know that this function, so I'm skipping some steps here because we've already used this example where we've shown that the function was continuous positive, eventually decreasing, and that the integral was converging, which meant the series was converging. So we're going to just jump right into finding what this remainder value of n would be. So we're going to say, okay, so I need the integral from n to infinity of x e to the negative x squared dx to be less than or equal to 1 over, and I'm going to use 10 to the third. So I'm going to bring this down here and get into this integral. So if we want to do that, we're taking the limit as t. This is an improper integral, so we have to use a limit. You cannot evaluate an improper integral without utilizing a limit. So this is the limit as t approaches infinity of the integral from n to t of x e to the negative x squared dx, and this side of the inequality is 1 over 10 to the third, and we're going to use a u substitution. We already integrated this when we did the actual example to show that this was a converging series, but I'm going to just run through it again. So this is just a little u sub u equals negative x squared, so then our du is negative 2x dx, and x dx is negative 1/2 du. Make the substitutions here. This is the limit as t approaches infinity, integral from n to t of negative 1/2 e to the u du. We want that to still to be, I'm just leaving the other side of my inequality here, carrying it down until I have computed the integral and the limit, found the improper integral here. So we'll keep going. This is going to be limit as t approaches infinity of negative 1/2 e to the negative x squared, evaluated. So I integrated and did my substitution, my back substitution in for the negative x squared, evaluated from n to t, still wanting this to be less than or equal to 1 over 10 to the third. And so this is the limit as t approaches infinity of negative 1/2 e to the negative t squared plus, because we're subtracting a negative, 1/2 e to the negative n squared. I forgot my bracket, 10 to the third. And we still want that to be less than or equal to 10 to the third. Now we take the limit, and this is going to approach 0, because we're letting t grow without bound. E to the negative t squared, that drops that into the denominator, goes to 0, and we end up with 1/2, and I'm actually going to write it 1 over 2 times e to the n squared. It needs to be less than or equal to 1 over 10 cubed. Okay, so I still need to find n, so I'm going to keep going here to find n. I can multiply and I can show that, let's see, 10 cubed less than or equal to 2e to the n squared. I'm going to flip this inequality and divide by 2, so e to the n squared is greater than or equal to 1,000 divided by 2. So I did a little bit of algebra there. I flipped things around, divided by 2, switched sides of my inequality, and expanded the 10 to the third, made it 1,000. So we're actually looking at, that's 500. And to solve for n, I can take the natural log of both sides, and n squared is greater than or equal to the natural log of 500. And take the square root, n is greater than or equal to the square root of the natural log of 500. All right, so pop that into a calculator. Square root of the natural log of 500 is actually 2.49. So n needs to be greater than or equal to 2.49. So to be clear here, that actually means we have to round that to a whole number because we're looking at the integers here for n. So n has to be greater than or equal to 3. So that's telling me that I have to use 3, literally only 3. Like I only have to use 3 terms in order to be accurate to 3 decimal places, to within 1/1000th of the actual sum of this series. So remember, the sum of the series means we're adding up an infinite number of terms. We've just shown that we only need to add up 3 terms. 3 terms. Really, that's not very much. We only have to add up 3 terms to be accurate to that amount. So part B tells me to actually find, sorry, I scrolled away again. Part B, I got so excited that it was only 3 terms. Part B says that the sum, find that actual sum accurate to 3 decimal places. So we have just shown that we only need to add up the first 3 terms. Okay, so here we just showed that n was had to be greater than or equal to 3, and so we'll just add up the first 3 terms, and we'll be accurate to 3 decimal places. So add up the first 3 terms. So let's find s sub 3. S sub 3, remember, is the sum from k equals 1 to 3 of k e to the negative k squared. So we're going to add up just the first 3 terms, and let's see what we get here. We get 1, that would be 1 over e, plus, and then we're going to have 2. Oops, sorry about that. No, I don't want to do any of that. Thank you for asking, though. Sorry, my computer was asking me for something there. And then we're going to have 2 over e to the 4th. And then we're going to have, plug in 3 over e to the 9th. And that would be the exact value, but if we were to plug that in, whoops, approximately, change that to an approximate, if we were to plug that in, we would get 0.405. And notice, I mean, it is pretty incredible. We only had to add up, when we talk infinite, I mean, like infinite should be a little mind-blowing, right? Like we're talking about infinite number of terms when we talk about an infinite series. And what we've just shown for this particular series, it turns out that we only have to add up the first 3 terms to get within 3 decimal places of accuracy on that sum. So that's how we can actually utilize these theorems to determine some estimates for the sum. Now, this was one where we didn't need very many terms to get very accurate, in fact. Now, there are other ones where we may have to add up more terms to have that kind of accuracy, but either way, we can still figure out how many we would need to add up, how many finite number of terms we'd need to add up to get to within a certain amount of accuracy, a certain amount of error. So that is our theorems, and we can look at some more examples during our class sessions on these.